Hey guys, today we're going to look at the limits of trigonometric functions. But before we can do that, we have to review the unit circle. Now the unit circle is called the unit circle because its radius is exactly 1 unit long. That's why as you go around the unit circle at the angles 0 radians, pi over 2, pi, and 3 pi over 2, your sine and cosine values are 1, 0, 0, 1, negative 1, 0, and 1 and 0, negative 1, simply because since you're going around, it does land on your x and y axis respectively. Now, as you go along, right, we did learn an acronym that we use to remember the signs of these trigonometric values. So if I were to have my axis, I taught you guys all students take calculus. So that means that in quadrant 1, all trig values are positive. In quadrant 2, only sine and its reciprocal, which is cosecant, is positive. In quadrant 3, tangent and cotangent are positive. And in quadrant 4, cosine and its reciprocal secant is positive. Now keep in mind that the x value is your cosine and the y value is the sine of your radian measure. In calculus, we're only looking at the radians, not the degrees. Now if you are evaluating for a trigonometric value, you don't necessarily need to memorize the entire unit circle. If you can remember quadrant 1, you're pretty much good to go, because as you can see, the cosine of anything that is over 6 is going to be the square root of 3 over 2. If I go around at 5 pi over 6, it's negative square root of 3 over 2, and that's because cosine is negative in quadrant 2. In quadrant 3, 7 pi over 6, the cosine is negative square root of 3 over 2, also because only tangent and cotangent are positive. But in quadrant 4, you see that 11 pi over 6 is a positive square root of 3 over 2, because cosine and its reciprocal are positive in quadrant 4. Now additionally, you will need to be able to look at a radian measure and determine what quadrant it's in. So there are patterns. In quadrant 1, all of your radian measures are pi over the denominator. And as you can see, the denominators are either 3, 4, and 6. In quadrant 2, the numerator is 1 less than the denominator. If you compare your radian measures in quadrant 2, if you look at the numerator is exactly 1 less than the denominator. So if the denominator was 3, the numerator would be 2 pi. The denominator is 4, the numerator would be 3 pi, and etc. In quadrant 4, the numerator is 1 more than the denominator. So if the denominator is 6, the numerator would be 7 pi over 4. I mean 7 pi, sorry, I don't know where that over 4 came from. But, and that's the pattern. In quadrant 4, the numerator is double the denominator minus 1. So for example, if the denominator is 6, double that, it would be 12 pi, and then you subtract 1 was 11 pi. So the radian measure, if that's over 6 in quadrant 4, would be 11 pi over 6. So those are just some tricks on how to remember the unit circle. And we'll go over that a little bit more as we keep working. Now, when we're trying to evaluate the limit of a trigonometric function, your first thing would be to see if you can plug in that angle measure and see if it gives you an answer. For these, that's exactly what we're going to try, which is the substitution method. We're just going to take whatever theta is approaching and plug it into the function. So for A, we have sine of 3 times 2 pi over 3. This is all the angle over 3 times 2 pi over 3. Over here in the numerator, the 3's cancel out, and in the denominator, the 3's cancel out as well. So now my simplified version of this function is sine of 2 pi, and it's over 2 pi. If you were to look at your unit circle, 2 pi is over here. It goes back to the beginning. And remember, because this is the unit circle, this is the coordinate 1, 0. The sine is the y value. Therefore, the sine of 2 pi is 0 over 2 pi. So 0 divided by anything would be 0. So the limit as theta is approaching 2 pi over 3 of sine of 3 theta over 3 theta is going to equal to 0. Now let's move on to this next one. We have the limit as theta is approaching pi of 2 cosine squared theta. Now keep in mind when you have the exponent directly following the trigonometric function. Cosine squared of theta is the same thing as saying cosine of theta, all of it is getting squared. It is not the same as cosine of theta squared. This would mean that the angle is getting squared and not the entire trigonometric function. Okay, so if we have the limit of theta is approaching pi of 2 cosine squared theta, we're just going to go ahead and plug in the pi. So we have 2 cosine squared of pi. Remember that this is the same thing as saying 2 cosine of pi, all of that gets squared. Now when you think of where pi lands, it lands right over here. And this is the coordinate -1, 0. The cosine is -1. So this means that we have 2 cosine of pi is -1, and then we square it. -1 squared is a +1, and then times 2 would be 2. So therefore my limit as of theta as it's approaching pi of 2 cosine squared theta is equal to 2. Now let's try this next one. Let's go ahead and plug in the 0, right? Because theta is approaching 0, and we get 1 minus cosine of 0 over sine squared of 0. If we were to do 1 minus cosine of 0, we get 1 minus, now cosine of 0, this is the coordinates. The cosine is 1 over sine squared of 0. Remember, that's the same thing as saying the sine of 0, all of that squared. The sine of 0 is 0. So squaring that would be 0. And this gives me with 0 over 0, which as we know, this would not exist. But in fact, for this particular limit, it does have a value. So we're going to try to figure out how to get that value. And how we do that is we're going to apply an identity. The Pythagorean identities are used pretty frequently, and you will have to remember them. The one that is probably used the most is sine squared theta plus cosine squared theta is equal to 1. But we also have 1 plus tangent squared is equal to secant squared, and 1 plus cotangent squared is equal to cosecant squared. So now how do we use them? If you ever see a trigonometric function that is being squared, maybe we can replace it with one of our Pythagorean identities. If I were to take our very first Pythagorean identity and I were to solve for sine squared, I would have to subtract the cosine squared. So that means that sine squared of theta would equal to 1 minus cosine squared of theta. So what I'm going to do is I'm going to take this sine squared and I'm going to replace it with 1 minus cosine squared. So I'm going to rewrite my limit as the limit of theta, as theta is approaching 0, of 1 minus cosine theta over 1 minus cosine squared theta. Now from here, you're like, okay, what do I do now? Well, this 1 minus cosine squared, this is a difference of squares. 1 is a perfect squared and cosine squared is a perfect squared. Therefore, we can factor it. So I'm going to rewrite this function now. In the numerator, I have 1 minus cosine theta, and in the denominator, if I factor it, would be 1 plus cosine theta and 1 minus cosine theta. These 1 minus cosine thetas would cancel. And so now I can rewrite my limit to be the limit as theta is approaching 0 of 1 over 1 plus cosine theta. Now I can go ahead and plug in the 0. When I plug in 0, I get 1 over 1 plus, and the cosine of 0, remember, 0 is over here. That is my radian measure, and the coordinate there, because it's a unit circle, it is 1, 0. So the cosine, which is the x value of 0, is 1, leaving me with a final answer of 1 over 2. Now let's see if we can apply that for this second one here. So the point of this is because if I were to just take pi over 2 and I plug it in, especially if you have a rational function, what I try is I always check to see if the denominator is 0. Because if the denominator is 0, that means that that limit would not exist. If I plug in pi over 2 into the denominator, I would get 2 minus 2 times sine of pi over 2, which is 1. And 2 minus 2 would be 0. Therefore, that denominator would be 0. And I'm going to see if I could rewrite this so that I would get a limit answer. Cosine squared can be replaced using one of these Pythagorean identities. If I were to subtract sine squared, I would get that cosine squared of theta would equal to 1 minus sine squared of theta. So that's exactly what I'm going to do. I'm going to replace cosine squared with 1 minus sine squared. So here we go. We have 3 times 1 minus sine squared, since I'm replacing that cosine squared, over, now in the denominator here, you'll notice that both terms have a 2 in common. So I can factor out a 2, and that would give me 1 minus sine of theta. Now, just like the previous example, that 1 minus sine squared, I can factor since it is a difference of squares. This would give me 3 times 1 plus sine theta times 1 minus sine theta, all over 2 times 1 minus sine theta. And here I'm canceling out that 1 minus sine theta, which is my problematic factor. So now I can go ahead and plug in the pi over 2. So I'm just going to rewrite my limit here. The limit as theta is approaching pi over 2 of 3 times 1 plus sine theta over 2. So I have 3. If I plug in pi over 2, I get 1 plus the sine of pi over 2 is 1 all over 2. In the numerator, we have 3 times 2, which is 6. And then when you divide it by 2, we get a final answer of 3. Let's try using a few other identities. What we have here are called the reciprocal identities. And that's because we're looking at the reciprocal functions for sine, cosine, and tangent. The reciprocal for sine of theta, or x, is cosine of x. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. Or you can also think of cotangent being cosine over sine, and tangent is sine over cosine. So here we have the limit of theta as theta is approaching pi over 2 of secant theta cosine theta all over 4 theta. The trick to these, if you don't have anything that's squared, we can't use a Pythagorean identity. That means we're going to have to kind of work something else out so that way we can find an answer. Now this one would have an answer even if you did just plug it in, but you would have to do a little bit more work in terms of figuring out what the secant of pi over 2 is. It's not that much more work, but just so that we can practice using these identities. What I like to do is I like to try to rewrite my trigonometric function there in terms of sine and cosine only. It kind of simplifies things a little bit for me and it's much easier to read. So secant is the reciprocal of cosine. So I'm going to take that secant theta and write it as 1 over cosine theta. And then it's getting multiplied with cosine theta. So see what I did? I just replaced this with that. And then it's all over 4 theta. The numerator could be further simplified since we have 1 over cosine theta times cosine theta. They cancel out. So what we have now is 1 over 4 theta. So that means I can rewrite my limit here as theta is approaching pi over 2 of 1 over 4 theta. And now I can go ahead and plug in that pi over 2. When I plug in pi over 2, I get 1 over 4 pi over 2, which can be simplified to be 1 over 2 pi. So now let's try applying some of these trigonometric identities. Okay, so for this first one, we have the limit as theta is approaching 3 pi over 2 of tangent theta cosine theta. So I'm going to first try to rewrite this using only sine and cosine. If you can kind of get into that habit, I mean, there are multiple ways of applying identities so that you can simplify your trigonometric functions. I like to follow a routine because that way I stay consistent and it's easier to do over time since you're practicing doing the same thing. So I'm always going to rewrite it in terms of sine and cosine only. So tangent is sine of theta over cosine theta, and we're going to multiply it with cosine theta. Now, before I move on, just so you know, okay, sometimes students get confused as to is tangent sine over cosine or is it cosine over sine? And the way that I remember it is I actually remember cotangent. I remember that cotangent is cosine over sine. I kind of think of cotangent, cosine. They both start with co. So that's how I remember that cotangent is cosine over sine. Therefore, if you're trying to find tangent, it's sine over cosine. So now that we have this written out, we see that these cosine thetas, they cancel. So I'm ready to rewrite my limit as theta is approaching 3 pi over 2, and it's of sine theta. Remember, think of your unit circle. 3 pi over 2 is down here. This is the coordinate 0, -1. The sine value is the y value, therefore this limit is equal to -1. For this next one here, we have the limit as theta is approaching pi of cosine theta tangent theta over sine theta. You can again work this out a couple of ways. I'm going to still choose to do write everything in terms of sine and cosine. So I have cosine theta, and then tangent, as I mentioned before, is sine theta over cosine theta, and everything is over sine theta. In the numerator, the cosines cancel. So all I have left now is sine theta over sine theta, which also cancel, so it equals to 1. So this means that the limit as theta is approaching pi of my simplified function, which is 1. It doesn't matter where your variable is approaching if you're trying to find the limit of a constant. The answer will always be that constant. Moving on to this last one here, remember we're writing everything in terms of sine and cosine. Secant is the reciprocal function for cosine, so I can rewrite secant as 1 over cosine theta minus. Now tangent is sine theta over cosine theta, and then we're multiplying by sine of theta. Now look what happens here. I see that my first term is over cosine and my second term is also over cosine. These are two fractions with a common denominator, so I can combine them as one fraction. This would be 1 minus sine squared of theta all over cosine theta. See, because I have this sine theta and sine theta over 1, when I multiply these two fractions, I get sine squared over cosine. So now I look here and I'm like, this sine squared looks very familiar. Now, just like how we can take our Pythagorean identities and rewrite a trigonometric function that's squared with 1 plus or 1 minus, whatever the case may be when you move things around, you can also move backwards. My Pythagorean identity that I'm referring to is when you have cosine squared theta plus sine squared theta is equal to 1. If I subtract this sine squared theta over to the other side, I'm left with cosine squared theta is equal to 1 minus sine squared theta. This is exactly what I have in my trigonometric function here. That means that that 1 minus sine squared could be replaced with cosine squared. So let's go ahead and do that. So I'm replacing that 1 minus sine squared with cosine squared of theta, and it's over cosine theta. Cosine squared just means that we have cosine theta times itself. So I could cancel out one of those cosines. So now I can go ahead and rewrite my limit, which I'm going to do over here in a separate color so you can see. We have the limit as theta is approaching pi over 4 of cosine theta. And if you have a look at your unit circle, the x value for pi over 4 is the square root of 2 over 2. Now we're going to have a look now at some very special limits. And now special limits are pretty much the shortcuts that we can take when we're finding limits of trigonometric values. So trigonometric functions rather, sorry. So for all of these, what we're going to do is we're going to find the limit as x is approaching 0 of f of x. I have given you the equation so we can look at the equation and compare it with our answers. But we're going to find the limit using the graphs. So for this first one, I'm looking for the limit as x is approaching 0, and I can see here that it equals to 1. For this second graph, as x is approaching 0, my limit is equal to 4. And for this last one here, the limit as x is approaching 0 is down here, which is negative 2. Now if I look at all of these equations, we have the sine of x over x. The special limit that we're looking at here is that the sine of x over x is equal to 1. And what you can do is if you have any coefficients attached to it, you would just do the operation. So if you have multiple coefficients in the numerator, you would divide it by whatever coefficients you have in the denominator. So here, since there's none, the answer is just 1. For this second one, we have sine of 4x over x. See, in the numerator, I have 4. In the denominator is 1. When I divide 4 by 1, I get 4. And for this last one here, I see my coefficients are 6 and it's over negative 3. And if I were to divide 6 divided by negative 3, I would get the negative 2. Now this is another special limit, and it involves cosine. Now let's go ahead and get the limit as x is approaching 0 for all of these. If I were to look actually just straight across, I can see that the limit as x is approaching 0 for all of them is 0. Now if you look at all of these equations, we have some sort of form of 1 minus cosine of something over x. And the same thing here, 1 minus cosine 5x over 2x, 1 minus cosine x over x. No matter what, as long as you have 1 minus cosine over the variable, your limit will always be 0. So these are my special limits. We have the limit as sine of some constant theta over some constant theta is equal to 1, or you would divide those constants. And the same goes for tangent. So it's the same thing. All right, if you have tangent of x over x, it's equal to 1. Now this also applies to its reciprocals. So that means that the limit as theta is approaching 0 of some constant theta over sine of some constant theta would also equal to 1. And the same applies for the tangent function. And then over here we have the limit as theta is approaching 0 of 1 minus cosine of an angle over that constant times theta is always going to be 0. Now important to note that these special limits are only applicable as long as theta is approaching 0. If theta is not approaching 0, you will not be able to use these special limits. So if I were just to re-examine some of those functions that we saw the graphs for, if we applied this rule, the sine of 4x over x would be 4. The sine of the limit as x is approaching 0 of 1 minus cosine 5x over 2x, this is this special limit, so it equals to 0. And finally, the limit as x is approaching 0 of sine of x over negative 3x, again, we divide those coefficients, and it would be negative 2. So finally, we're going to go ahead and practice using our special limits. For this first one, we have the limit as theta is approaching 0 of 2 sine of 5 theta over 3 theta. So basically, we're going to take all of those coefficients in the numerator and we multiply them. 2 times 5 is 10. And we divide it by the denominator, which is 3. Since I can't divide, we're going to leave it just like that. Now for this one over here, this is a little bit different. I can tell that this part here looks like a special limit. This part here also looks like a special limit, but everything is over theta and it's being added together. Well, since everything is over the same denominator, we can actually split this into two separate fractions with the same denominator. 1 minus cosine theta plus 2 sine theta is the same thing as 1 minus cosine theta over theta plus 2 sine theta over theta. See, if you were to add these together, what do? We add the numerators, but the denominator doesn't change. So this would still give me the same function that we have written above. So now I can go ahead and apply my special limits. 1 minus cosine theta over theta is 0. 2 sine theta over theta, we just take that coefficient, which is 2. 0 plus 2 will be 2. For this one over here, we have theta times cotangent of theta. Now, in order for me to use any of these special limits, they're only in terms of sine, cosine, and tangent. So I'm going to rewrite cotangent in terms of tangent because I think that this will look very similar to one of my special limits. Keep in mind that cotangent of theta is the reciprocal of tangent, so it would be the same as 1 over tangent theta. So what I'm going to do here is I'm going to replace this cotangent theta with 1 over tangent theta. And that would give me theta times 1 over tangent theta, which is the same thing as theta over tangent theta. And this is my special limit. Remember that I said that these special limits not only apply to tangent theta over theta, but as well as to its reciprocal. And it would still give you the same answer. So this would be 1. Now for this last one, looks a little bit more complicated. I can see that none of this it kind of resembles my special limits, but I'm not quite sure. So I'm just going to see what I can do. And a lot of working with trigonometric identities is sort of playing around with them and seeing how you can rewrite it so it looks familiar. Eventually, when you do this enough, you do pick up on patterns. Like for this numerator, I noticed that both the first term and this second term have a sign in common. So what I'm going to do is I'm going to factor out sine of theta from both terms, leaving me with 1 minus cosine theta. Then the denominator is theta squared. Now remember what happens when you're multiplying fractions. When you're multiplying, it's not the same as addition or subtraction where you just add or subtract the numerators and leave the denominators the same. For multiplication, you multiply the numerators and multiply the denominators. The numerators here, sine theta and 1 minus cosine theta, resemble my special limits, but the denominator is theta squared. So just like how in part B I separated into two separate fractions, you can also separate this as two separate fractions. So I can rewrite this to be sine of theta over theta times 1 minus cosine theta over theta. This is the equivalent to this. I mean, if you think about it, if you were to multiply this out, you will get sine theta times 1 minus cosine theta all over theta times theta, which is theta squared. So this is indeed the equivalent to my original function. And now I can go ahead and apply my special limits. Sine of theta over theta is 1. And 1 minus cosine theta over theta is 0. And since they're being multiplied, 1 times 0 is 0. And that's all, folks. That's special limits.